Walaikum assalam.
Hi, Professor.
Hey, yeah.
I just wanted to ask a question.
Sure.
Because some of us applied through the 410 that they.
Yeah.
We're not in the.
Yeah. On iLearn, you mean?
Yes.
Yeah, I got the full list from Zere, so I will add you. In fact, I was trying to add you before the lecture, but there was some problem with the sheet.
Right.
After the lecture, directly will be added.
Okay.
But I have the full list, so don't
Okay.
worry about it.
Thank you.
Yeah, thank you. Were you assigned like a particular lab section, like you were asked to? Okay. Okay, but who gave you the lab section? Desiree? Like, okay, yeah, thank you.
ايوه شفت. وكان زحمه الفايل بتاعه وانا مش عارف. شفت لما قلت لك شفت اللي هو صح بس ما في لو اوكي مثلا في طريقين يعني لو في طريقين اللي هذا بضيع الله
Good morning, everyone. So last time we stopped here. So let's retreat a little bit, then continue. Just to again to remind you of what is the bigger picture, what we have been doing so far. Is we kind of slightly change your mindset about what is an embedded system, then open your mind for the general applications that we have nowadays, like the modern practical industry challenges we are facing. How embedded systems are more performant at the moment and there are new challenges. It goes beyond like a simple Arduino and a big microcontroller, right? There's something more to learn about embedded systems than the core one. And then we started looking into some of these opportunities, applications, but also some of the challenges, right? And today we'll continue some of these challenges and see how we can address them, right? This is very important because this is the bigger picture that includes how we're going to continue the course up until the end, right? Every single lecture we're going to take is in fact in addressing all of these challenges, right? So we will always go back and say, okay, we're doing that because we want to achieve, for example, safety or predictability or high performance. Good. One of the things we mentioned last time is one solution to address some of these challenges, mainly the mixed criticality nature. Do you remember when we said modern embedded systems are mixed criticality? In a car, you have something like a very safety critical task like the airbag control unit and engine control and the cruise control. There's something that is not critical at all, like the infotainment unit, the connectivity, right? And both are running on the same platform. How do we really meet the requirements of these different critical tasks? Well, one of the solutions that everyone is adopting at the moment in industry, well, as well as academia, is to do it or to use heterogeneous multiple processor systems on a chip. Why this makes sense? This is what we stopped at last time. As we said, because if you have a heterogeneous system on a chip, you have multiple processing units. Every one of these has its own features, its own strength, right? So for example, a CPU can be more predictable than a GPU. Predictable means it's easier to analyze, right? Even CPUs themselves, as we will see in one of the examples, they have different types. Some of the CPUs are simpler for timing aspect, and they are not that performant, right? Some of the CPUs are very high performance, but they're very hard to analyze. Then GPUs, for example, we all know that they are used for video processing, right? Machine learning applications. Then we might also be deploying, well, data signal processing for sensor data fusion and ASIC controllers. So you have multiple type of processing elements that you put on the same platform to see for every task, what is the suitable what is the suitable CPU that you want to run this task on. Good. And all of these are in fact sharing the same platform. Good. So this is simply, you can think of it as that this is the current and future of embedded systems, right? You deploy a very high performance system on a chip to address all the tasks running on this system, right? This is what we stopped at last time. No. Interesting. Okay, should be good. What? I think this projector, we had this issue last time as well, right? This projector has a problem. Okay, should be good. Some animations, the projector is flickering through them. Okay. So to give you a practical example of heterogeneous system on a chip, did we go to this slide last time? No. So simply, this is a multiple processor system on a chip from Xilinx. Xilinx is purchased by AMD right now. If some of you know Xilinx is in fact an FPGA company, right? They manufacture FPGAs. But interestingly, they don't only manufacture FPGAs at the moment, similar to everyone in the industry. They try to develop also systems on a chip, and they target automotive. This is one of the very famous platforms used in automotive, right, by many embedded companies. So if you look into this platform and the types of the processors we have there, then simply you can find we have two types of ARM cores. We have an ARM, what we call E53, it's an application core, so it's a high performance core, right? Usually this is used to run tasks that is requiring high performance, right? And then we have also a real-time core. This is usually a simpler core, less performance, running at a lower frequency. You can see that this is, for example, a 64-bit quad-core processor with virtualization, so okay, top of the performance, but this is only a 32-bit, similar to embedded devices, and it's only dual core, right? So it's called RCS from ARM, and it's targeting real-time. And then we also have a GPU, interestingly, on the same SoC, to also target the machine learning, camera processing, and sensor processing. And then we have the FPGA, the programmable logic, right? FPGAs are currently used also as accelerators to deploy machine learning algorithms on the RTL. Did you guys, I think in your digital design, you write some very low VHDL? Oh, this is a course that you're taking now? Okay, and the intention in the lab is to do some RTL development? You don't know yet?
Yes, that comes.
Okay. So basically, well, to be honest, that's a little bit surprising that until fourth year, you didn't really write any HDL. But hopefully this course you will do, like not this course, like the other course, the advanced digital design, if I remember correctly. Yeah. So simply FPGA is used to, you write your own IP basically, your own simple processor, right? Your own accelerator. You start from address and then you deploy something like more complex. And FPGAs are currently also very widely used in embedded systems, because you implement your own hardware, so it's more predictable, right? And because it's massively parallel, it's also good for performance, right? And then you have some other kind of ASIC processors for security, for encryption, for Wi-Fi connectivity. So you have all the types of the processing elements we discussed in the previous slide, right? And this is simply currently deployed again in many applications for embedded mini automotive. Are we good? So this is a practical example that is very famous. So this is a less famous platform from another company from Asia, but it's pretty similar. The key idea is you have CPUs, but you also have like a real-time CPU. Let's see what it is. Yeah, here there's a real-time domain where there's a real-time CPU, non-real-time CPU, and then there's a GPU, all on the same platform. Good. So now, does it mean that by deploying systems on a chip, we have solved all the problems? Well, in reality, no, right? Systems on a chip on their own bring their own challenges to embedded systems, right? So we'll go back to some of these challenges. We spend a little bit more time and thinking about them in discussions, and then we will see throughout the course, as I said earlier, how we are going to address these challenges. So the first challenge is safety, right? And safety is a big umbrella in embedded systems, as we'll see. We call them safety critical systems, right? So these are systems that simply we care about the safety. And how did we define a safety critical task last time? How do we really determine whether a task is safety critical or not? Does anyone remember?
The response time?
Response time is the timing angle. Like it's like there is a, so we said it's a real-time system, right?
Then the amount of damage it will cause.
Exactly. So it's the consequence of failure, right? So the way most standards, certification, again, avionics, automotive, healthcare, whatever it is, aerospace. So simply they define the level of the criticality of the task based on the consequence of failure, right? So they tell you, for example, if the airbag fails, what is going to happen? I've seen this animation last time, I think, right? You're going to lose the driver life, right? So this is a high criticality task. Then what if the infotainment unit, what if your Wi-Fi connectivity doesn't work or your video player on the screen in the car doesn't really work? Not big of a deal. So this is a lower criticality task, right? So we define the safety criticality level of the task based on the consequence of the failure. And we said from different domains, there are different criticality levels. In automotive, for example, we said there are 5 criticality levels, right? From the highest to the lowest, E, B, C, D, E, right? And then in avionics, there are also 4, ASIL, E, B, C, D. Good. So how do we ensure safety? Or first of all, why safety is a challenge in safety critical systems? The first one is you cannot really trust the communication channels. So the channels. So if we go back to this platform, something like this, maybe go abstract a little bit into the same slide that's going to be wrong. Good. So here, if we go to this abstract view of a system on a chip, assume I'm running a highest criticality task on this CPU, okay? And then there is a non-critical task running on the GPU. The problem is that both are in fact sharing the interconnect, right? Sharing the communication channel, right? So if you share the communication channel, then the critical task on the CPU is in fact susceptible to attack, to interference, to contention from the non-critical task, right? You see the problem is that now you are deploying both critical and non-critical tasks on the same SoC, which means the critical tasks, in fact, are impacted by the non-critical ones, right? Most of the challenges we will see later on is coming from this sharing of resources, right? I'll try to go back to a trap. Good. So the first problem with safety is I cannot trust the communication channel, right? So we will see a very interesting example about security, even in modern cars right now, not fully autonomous, not anything, something is already on the streets at the moment, how in fact sharing a communication channel between a critical task and a non-critical task can cause a big of a problem, right? And then the second biggest challenge for safety, this is maybe a challenge that maybe you don't expect, which is us, right? So not fully autonomous systems or even autonomous systems, one of the definitions of an embedded system is interacting with the physical environment, right? A very big unknown in this external environment is human beings, right? Because we are very unpredictable by nature, right? Again, there is an autonomous car on the road, and then all of a sudden a pedestrian is really crossing the road, right? Or maybe another driver is not behaving as supposed to be, and then basically taking like a sudden left turn or something, right? So the uncertainty on the human being actions, which is very natural to really our nature, right? we're not really computerized. So we are not really saying 1 + 1 = 2 all the time. We're not very logical most of the time, right? So your actions are very unpredictable, which in reality are most of the causes of the issues when it comes to autonomous systems. I'm not sure if we last time again mentioned this or it's going to come in one of the slides, but I think not yet. It is coming to one of the slides. More than 90% of the issues, for example, in avionics, is not because of the autopilot. There is a problem with the computer. It's because of the pilots themselves, the human beings, right? 90% of the failures in airplanes at the moment are attributed to the human pilots, right? They are taking action that they were not supposed to take. Okay? So you cannot really trust the users, which is a big problem in embedded systems because you interact with the users all the time. So you will see in these few slides, we're going to talk a lot about problems, and then later on we'll think about solutions, right? So if I cannot trust the communication channel because of the non-critical task, I mean, it's in fact makes more sense that I don't trust the lower critical task itself, right? If you think about a pacemaker, this is a block diagram of a simple pacemaker. Do you know what is a pacemaker, right? You regulate the heart rate of patients with heart issues. Now, a very simple pacemaker is just doing the regulation. So it's only one very safety critical task. But most modern pacemakers, they have other things to do. For example, they might have connectivity, either Bluetooth or RF or whatever, to be able to get in data from the pacemaker without really taking it out, right? So they have some connectivity. Also, they have some logging tasks, right? A logging task is simply a task running on the background that simply, for example, stores the samples of the heart rate, right? To tell the doctor whether everything is going okay or not, or there's some sort of an alert, right? So most pacemakers started implementing some sort of intelligence, right? The problem is this logging in the background task is non-critical. Talk about connectivity, for example, it's connected to a Bluetooth or something. Through this connectivity, it can be hacked, for instance, right? And now if it's running on the same platform, running on the same hardware, the same chip, as the task that is regulating the heart rate, then you can imagine what consequences could happen, right? So I cannot really trust any non-critical task, right? Some of the modern standards, for example, avionics, I'll keep saying, automotive, I'll keep giving automotive as a very practical example. In automotive, they tell you, if you are running a critical task, a non-critical task, and they share, for example, a CPU, you must certify the non-critical task at the same level of certification as the critical one. So what do they do at the moment? They tell you, well, they start sharing resources because you cannot trust the non-critical task. You have to consider it as to be a critical task, right? So that's really their way out to solve that problem, right? Why they are doing this? It's way more costly and a lot of hard work for the non-critical task. Not because of the non-critical task itself. It's good because they know it can be a vulnerability that is used to, in fact, target an attack or have a problem with the critical one. Okay? This sharing between critical and non-critical, we're going to see its impact on scheduling, its impact on security throughout the course. Is there any question so far? Yeah.
Then how do you trust any device that connects to the internet or Bluetooth in general if you can't keep back?
Yeah, that's in fact one of the biggest problems in connected embedded systems, right? Is that how can we really trust if it's connected? One way to say is I will develop tasks that are connected, that are completely isolated in hardware from the critical ones. They don't communicate anything through hardware. But now, if they don't really communicate, you take out some of the functionality, right? So you will see that it's a circle of trade-offs. You want to impose safety and predictability, you either take performance or functionality, right? If you want to introduce more functionality, then it's more susceptible to interference and hacks and issues, right? Yeah, so it's not an easy problem to solve. So how do we ensure safety? What people really do in industry to ensure safety? The first thing is formal verification, right? What we mean by formal verification, simply the standards, the certification standards in automotive, for example, they tell you an airbag task, it's the highest critical, or engine control is the highest critical. You need to write math proofs, in fact, to ensure that under all worst case scenarios, you will never exceed, for example, your deadline, right? So there is a formal proof, what usually used not like through paper and pen, but through automated tools, right? There are commercial automated tools for this verification that simply gives a proof, a mathematical backed proof to the certification authority that this task is totally safe under all scenarios. Why formal verification is sometimes especially for the highest critical levels, is the way out. Because through formal verification, you don't need to redo testing under all scenarios, right? Once I formally verify I'm good, no matter what else is outside the environment, you can ignore the environment completely, right? What is the problem with formal verification? It can work for a simple system, but for a system that is as complex as a self-driving car on the road with all the uncertainties, how can I really formally verify all the hardware and all the sensors and cameras in that car? It's almost impossible, right? It's an NP-complete problem. Hopefully you hear that term in algorithms or data structure. Do you know what is an NP-complete problem? It's a problem that you cannot solve in linear time. So there is no solution for, right? You guys took a data structures course, I would assume, right?
Yeah.
Did you know what is a big O notation?
Yeah.
Right? So there are problems that we call, like there are P problems, which means they have a solution in linear time, this linear time, even if you take a little bit more time, but there is a bound solution for it. And there are solutions that there is no known exact solution for in the meantime, right? So it's called an NP-complete problem. So there are formal proofs that in fact formally verifying a complex system is an NP-complete problem. It cannot be solved given the mean we have nowadays, right? And then what certification? We talked a lot about certification. So certification is simply a process-based mechanism that asks you to do testing. It asks you to do real road tests, for example, for automotive, do maybe simulations and mix all of this in some sort of a certification process, right? For example, in avionics, the certification standard is called DO178A. And then this is, I think, is electronics for healthcare. For automotive, it's ISO 26262. The problem with certification, it's a very tedious and very expensive process. It takes 2-3 years and few $1 million, right? It's not a simple task.
Oh, what's that?
Yeah.
For the formal verification, so we'll just test if the math on the system works fine. Is that it?
It's not about the math of the system. It's more about you use the math to prove that the system is fine under all scenarios. So a typical example we'll see in this course is when we go to scheduling, we will see that how we really write schedules that simply proves that the task utilization is always scheduled. Like you will always meet your deadline, right? This is called the formal proof.
And how does that ensure safety?
Yeah, because for example, from a timing angle, if I give you a formal proof, a mathematical proof that my task will always meet the deadline, regardless of what is happening in the system, then you are good. You are going to buy this from me, right? You are telling me my airbag will never exceed the deadline under any scenario, mathematically proved. I'm good, right? So a very nice example. There are 2 examples here in the slide, but we can talk about one of them only, and then you can read about the other. So even if you formally verify a system, because we said formal verification and certification is a very tedious process, even in very big and expensive systems, embedded systems, most of the time some failures can happen during runtime, right? Here is a typical textbook example from F22. So I think earlier we had a slide that F22 has like a 1.5 million lines of code. It's a very complex system. It's a multi-million-dollar embedded system. Then in 2007, this is an incident of why, in fact, not verifying all the system angles. And even if you spend many years in trying to make the system correct, you might forget something that seems from outside, right? As a hand sign. So here in 2007, there were like a swarm of F-22s, 12 of them, going from Hawaii to Japan. Why this journey was very interesting? Because Hawaii, if you know the map, Hawaii is really the far west of the Earth, right? Then Japan is the far east, right? So going from here to there, you're going to cross what we call the international day line, right? So simply on this exact same moment, if you are, for example, today is what? Tuesday. So if we are Tuesday in Hawaii, this is in fact Wednesday in Japan, right? Because of the time difference, right? Like through Hawaii is called the last time on Earth, and in the Japan, this is the first time. Now, a very silly mistake on those systems, simply what happened is that once all the 12 ones crossed the international day line, simply the GPS is telling them that you are in a different location, and you basically calculate your data and timing based on where you are, right, through the GPS, right? But once you cross the IDL, you realize that you are in a completely different day, which is something that wasn't accounted for in the software of the system. They didn't think of, I can really go back in history or go back in the time or move forward in the time, right? So you're not expected simply the clock is just the clock. You move every minute and then an hour and then the day, etc., etc. But just suddenly crossing a day, whether in the back or in the future, something wasn't accounted for as a corner use case, right? What really happened due to this is that the software crashed. The operating system of these 12 ones really crashed, right? Then at the end, they managed to really land in some sort of an island. But you can imagine that this is a corner case that to us, it might sound very silly mistake, but it wasn't accounted for in such a complex system, right? So it's why it's very important to spend a lot of time and effort in verifying embedded systems and systems in general. Good. Okay.
So in that case, Professor, they didn't do the certification.
Well, this in fact, what you must do. This is a military certification, so it has its own really domain. But the point is that even with certification, even with so many years, you can really still have corner cases that really are not really accounted for. This thing is like this. Good. So this is why, as I said, it's very important to put in a lot of effort in the development cycle on verification, right? If you look into like a practical system or a chip, especially in embedded system, you find that we spend more than 80% of the development, including the number of hours, the money spent, as well as the manpower put into the development in verifying the system, not in really implementing and designing it, right? Only 20% goes to design and 80% goes to verification, right? About the safety challenge and why verification is important, also why verification is a challenging task. Now, the second challenge is predictability, right? What we mean by predictability, we said embedded systems are naturally real-time systems, right? And the way we express that they are real-time is we said their functionality their correctness does not depend only on the correct functionality, but also depends on the timing of this function, right? Do you remember this statement? This is a very important statement for real-time embedded systems. I will say it again. So the correctness of the system does not depend only on the correct functionality, but also on the timing of this function. What do we mean by this? We gave the example of a MATLAB code, like a general purpose system, that if you wait for a minute and you get the correct result, it's pretty much the same as you wait for 2 minutes and you get the correct result. At the end, the system did its own task, which is giving you the correct result, right? But on the other side, in the airbag, if the airbag, instead of opening in 1 millisecond, it opens in 1 second, well, is it any useful? Not at all, right? Despite the fact that from a functionality perspective, it opened, right? So it did what it was supposed to do, but not within the timing frame, right? So this is why timing is very important for the correctness of a real-time system, right? So now, how do we ensure timing? This is why we call them real-time systems. How do we ensure timing? Through something called predictability, right? You want to ensure that your system is predictable, right? Why predictable? Because predictable means its behavior is known from a timing angle under all possible scenarios, right? Under all worst case scenarios that can happen really in the environment. For example, I will never exceed my deadline. Good. Now, if we look into this layer of an embedded system, this is from a very famous book. It's called Cyber Physical Systems book by Professor Edward Lee. One of the very dominant, like he's a Berkeley professor, and the dominant figures in the field. He's the supervisor of my supervisor as well, so I know the guy personally. So simply, I took this picture from his book. If you look into this picture, the main idea behind the picture is they talk about an embedded system as a layered system, right? If you remember our lecture 0, this really reflects back to our like computing system layers that we discussed in lecture 0, right? You start from the very low layer of VLSI, and then you end up on the highest layer of an operating system and an application, right? The same thing for an embedded system. You start from the transistors, and then you end up in multiple applications running on the platform, right? Now, the key idea here is if we care about predictability, if you look into the transistor level, the circuit level, there is no uncertainty at all. Everything is predictable, right? If you give, for example, to an AND gate 2 inputs, the output is expected completely. And also its timing, the propagation delay throughout the gate is known deterministically, right? It doesn't change. For example, I take, 1 microsecond to give you the output. And this time is constant because that's the propagation delay of the circuit. So where the uncertainty comes from? Where the unpredictability comes from? It doesn't come from the hardware. It really comes from the interaction of all the applications running on this hardware, right? So for example, we said multiple tasks running on this platform, on this circuit. Those tasks can really compete for resources. There is a single CPU, there are 3 tasks running. Who is going to access the CPU at the moment? The other 2 tasks will be delayed, right? So we'll have here an example of how really this sharing of resources, we already defined logical and temporal correctness. So let's have this example to understand really the unpredictability source. So assume you have a system on a chip with 2 cores, okay? And then because you have a critical task and non-critical task, you will say, I want to isolate them, right? So I want to give 1 core for the critical task and another core for the non-critical task, right? So today I have my bench, I think we can draw some stuff. So let's say I draw something like this. So you have 2 cores. So this is core 0 and this is core 1. And you say, well, I care about predictability. I was taught in 411 that I should isolate the critical from the non-critical. So simply I say, give 1 core for the non-critical task. I will call this non-critical, and give another core for the critical one. Good. Just to ensure that they don't compete for the CPU. Good. Now, did you solve the problem? Well, in reality, not. The reason is in a modern system on a chip, those CPUs, these cores have their own private caches, L1 and L1. I hope you guys from your architecture course know what is a cache, right? And then there is a shared cache between the 2 CPUs. We call this the last level cache, right? So in almost all modern systems on a chip, there are private caches for the cores, but there is also a shared cache before you go to the main memory, right? This is your main memory. Now, even if you really isolated the cores, I will give you an example that the non-critical task running on a completely different core can in fact impact the critical task, right? So let's have an example that the critical task is requesting to access a piece of data that I will call cache line A, okay? Assume cache line A originally was in the LLC, the last level cache. So you go access it from the last level cache. Assume that the last level cache access time is 10 cycles, for example. Okay, so the critical task will go to last level cache, ask for A, takes 10 cycles, and then bring A and continue, right? Now, after some time, the critical task will ask for A again. But before this happens, the non-critical task, let's say it's requesting B does not exist in the last level cache. So what is going to happen if you access a cache line that is a miss in the last level cache? Go to the main memory or next level of cache, right? So you are going to bring B from the main memory. When you try to put it in the last level cache, the last level cache is full. I have to replace something. Assume according to the replacement policy, you have to evict A. So you remove A and you put B. Let's say it's the least recently used, right? For example, right? Well, regardless of the policy, there is a possibility that A can be removed, right? Right? So now, in the next time, so if I draw a timeline of the non-critical task and the timeline of the critical task, the critical task first here requested A, and it took 10 cycles. Before it requests A again here, in the meantime, the non-critical task requested B and replaced A. So A was removed from the last level cache. Now, when the critical task, and it took a lot of time, let's say 200 cycles because of the main memory. Now, when the critical task is trying to ask for A, what is going to happen? It's not in the last level cache. I have to go to main memory, and then I will take the large access time of the main memory. Instead of 10 cycles, I will take 200 cycles. Yeah, that's an excellent question. How does it make a difference? What really happened here? Assume, to know this, assume that the non-critical task did not exist. What was going to happen? It will stay 10, right? So when you calculate your timing, remember, in critical tasks, we care about that in your execution time, you must really meet your deadline, right? Now, to be able to meet my deadline, I need to calculate my execution time and ensure it's less than my deadline, right? Now, without the existence of the non-critical task, how do we calculate this? I have cache hits, cache misses, I add things up, I'm safe, I'm good. But there is a non-critical task competing with you, turning out some of your cache hits into misses. How does it impact things? It increases your execution time.
Okay, so yeah, you're accounting for the time it went and what.
Exactly, because you have, I mean, right now, I didn't really get A up until waiting for 200 cycles, right? Now, why did this scenario happen? Because these non-critical and critical, despite running on two different cores, they share a hardware resource called last level cache, right? So what is the final result? The final result is that the critical task right now, its timing depends on the non-critical task behavior. Because maybe, is this guaranteed to happen all the time?
No.
Maybe no. Maybe the non-critical task will never ask for B, and then I only suffer 10 cycles. So now there is a variability that is really happening. Am I going to be a hit or a miss? I don't know. And how do I know this? You cannot know this only by looking into the critical task. You have to also look into the non-critical task behavior. But the non-critical task, I don't certify, I don't analyze, I don't care about, right? So you see that dilemma here? So your behavior, so people express this formally in real-time systems by saying the behavior of a critical task now depends on the behavior of a non-critical task. So the timing behavior of the critical task depends on the non-critical task. This dependency breaks certification. Because at the end of the day, this non-critical can impact you, right? For example, if this wasn't really certified or secure, an attacker can try to really do something called denial of service attack. It tries to push in a lot of traffic from the non-critical task to ensure that the critical task keeps waiting forever, right? So now you are susceptible to interference, right? We call this timing interference. Is that clear? We're going to have lectures about this specifically, like for cache analysis and real-time systems, but I just wanted to give you like a teaser of the challenge, right? How, in fact, non-critical task running on another core can impact me, right? That's because of the shared resource. If that's not clear, please ask, because this is a very, very critical point for the course.
So why can't I just split everything?
An excellent question. That's one of the solutions, right? But now maybe, again, to continue this discussion, what are you losing there if you do this? You lose performance.
Yeah.
Yeah, you lose performance and communication as well, right? So we'll come into those solutions, right? We call this partitioning, ensure that, well, I don't share anything. But is that clear enough? Now, is the last level cache the only shared resource?
No.
No, there are other shared resources, right? We have interconnect, we have main memory, we might have other levels of caches, we have the IOs and sensors and actuators, right? So all these shared resources are in fact source of interference that we need to analyze, right? So a big of a deal of a job of an embedded system architect is to ensure that all the hardware components, you can ensure predictability to make sure your worst case time is within the bound. Are we good? You guys are way quieter than the other section, so I wasn't very sure if that's because you understand what I'm saying, or that's because you are losing hope. Yeah. An excellent point. Well, in reality, yes, because when I say accessing A or accessing B, this might be because within a for loop, you take a path or another path, or an if condition, you take a path or another path, right? This is called control flow graph, right? So analyzing the program itself. But the program really depends on the input set, right? If I'm receiving a certain camera, like camera input, a frame from a camera, and if someone is passing like a pedestrian, and then I capture well, let's take an easier example. In an airbag, whether there's a crash or not, you will exercise different paths in your program. And it simply means your behavior will be different for the cache, for instance, right? So yes, all of this, in fact, depends on the input set. And the input is coming from the environment, which in fact makes the problem even worse, right? Any other question? Okay. So we said that there are so many other resources, including interconnect and caches. So just to show you how complex is this in modern systems. Previously, and again, I'm taking the automotive always as an example. In current cars, we said there are ECUs, like simply one ECU for every task, right? We said we have hundreds of ECUs in our cars, right, at the moment. For example, there is ECU for airbag, ECU for door lock system, ECU for ABS, ECU for cruise control, engine control, whatever you think about, right? The way those systems are architected at the moment for traditional cars, right? I would call them traditional cars, is that simply there is ECU for every task, and they only communicate through what we call an off-chip network, right? In a car, for example, this is called the CAN bus, right? Like that's the most famous interconnect in cars. It's called the campus. But there is a trend to move from this to a more consolidated system. Last time I showed you the Tesla chip, like I said, lecture 0, where there's a big system on a chip. There's a central CPU that really takes everything, right? And the reason we want to centralize stuff is we said this is no longer scalable, right? If I move to autonomy, I need more ECUs. I cannot really have thousands of ECUs. You can no longer really communicate through a shared bus, right? So what do we do is we move from what we call a multiple single core systems. Well, because this is a system on its own, it's a system on its own, a system, and every one of these is a single core, right? A simple microcontroller or ECU. We're moving to what we call a single multi-core system, which is our SoC that we have seen earlier. Now, there are multiple cores, and these cores, instead of sharing an off-a-chip network, they really share an on-a-chip network and I/O devices and memory and interconnect and everything, right? Which means the problem we're talking about caches and memories and interconnect becomes more relevant nowadays than what it was before, right? In reality, even with this off-a-chip sharing with bus, I have an example later on in security that still this sharing can cause issues, but it can cause way less issues than if you really share more resources, right? So the trend is you are moving more towards sharing resources among different tasks in an embedded system. Why this is a trend? Simply for scalability, for cost, and for improving performance. What is the trade-off? What is the expense? Is you are complicating predictability. Right? It's very hard to analyze this system compared to this system. Okay. And this thing need to be fixed. I just fix it and update the slides. So if we look into this multi-core platform, then we said, well, shared cache is the example we looked at, but there are also shared interconnect, some other cache levels, and a main memory system. All of these are in red because they are source of interference, source of contention. Okay? So you need to analyze them. Great. Then another embedded system challenge, which is sometimes put under the umbrella of safety, is security, right? So why security is another challenge? Again, because of sharing resources, right? If you start sharing resources, well, even if you secure the critical task, what we call the secure domain, the security language, there is a non-secure domain that is sharing the resource with you, right? A very interesting example I usually give in lectures. Projector. So there are many examples here from news, like baby monitors and smartwatches for kids. But the most interesting one, most interesting tool, is this one. We're not talking about a fully autonomous vehicle. We're not talking about a sci-fi movie. This is something that really happened in the cars that are on the streets. So simply what happened is that researchers, I think this was 2016, assume you are driving your Jeep Cherokee on a highway, and then they were able really to control the wheel remotely, right? So what happened is that you are driving, but then you're trying to take, for example, like a move to a right lane or take a right left or a right turn. Well, they force you to go to the left. How did they manage to do so? Well, we'll see in a second. But more interestingly, the year after, they showed another experiment where they were able to stop the engine completely, right? So you're driving your car, maybe like 120 kilometers per hour on the highway, all of a sudden the engine stops. It's very scary, right? But the engine control, we said, is a safety critical task. How did they manage really to hack or to have a security vulnerability on? What they really did is they managed to hack the radio unit. The radio is part of the infotainment. The infotainment is not critical at all, but it should be isolated from the critical task, right? So if we go back to our in this projector. Yesterday, this wasn't the case in the other room. Okay, so if we go to this system here, assume that the radio unit ECU is in this node, right? We call these nodes in automotive. And assume your engine control is this node, right? Now, this is fully secure. I cannot really, it's sometimes called air gapped, like it has no connectivity at all, so it's safe, right? Because this is not a fully autonomous car. But this one I can access through the radio, right? It has some connectivity. So they hacked into this and used it to send malicious scan buckets, we call this scan messages, simply on the bus to the engine control to stop it, right? So if you see the root cause of the issue, it was because of the shared network between the critical and the non-critical task, between the secure and the non-secure task. Good? So sharing resources can cause variability that is really addressing or causing a predictability problem, but also can cause vulnerabilities that really can cause huge security issues. Yeah? And again, this is even without talking about a fully autonomous vehicle that's connected and then communicating with the traffic light or connected to the internet. We're talking about a normal car in the street, right? And well, more or less 10 years ago. Good. There's a very nice video on YouTube. You can look it up. Another interesting example is this nice paper. And again, there are videos on YouTube about it. So simply, we know that most modern cars, they are keyless, right? What does it need to be keyless? You don't really need to physically insert the key into the door to open, right? How does it really happen? Well, there is communication between the electronic component, the embedded system you have in the key, and the electronic component that you have in the door, right? This communication can be RF communication or something else. So what they did is they managed to intercept this signal. So basically, well, hack into the communication channel, intercept the signal, copy it, and then later on repeat it, right? So once you really get in the message and you are able to repeat it, then you can really open the door, right? So even if you lock your car, this is why you titled the paper, lock it and you still lose it, right? Interestingly enough as well, it's not only researchers and like geek engineers that are doing this. Thieves on YouTube, you'll see them having a lot of videos about this, right? There are really very interesting camera prints, like or camera footage from police that's showing really thieves, at least in North America. They are smart enough to really do this, right? Because this is a very low cost system. You don't really need something that is $10,000 to have a repeater, right? Sometimes using tens of dollars of an embedded device, you can really replicate this experiment, right? I wouldn't really suggest you to do, but yeah, it's something that's really happening. Again, what is the root cause? What do you think of? You are now like an embedded system engineer and trying to see why did this really happen? It happened because of the communication channel, right? How do we address this? Well, there are many solutions that people try to deploy it now. When this became very famous, what they did is the companies weren't really encoding the messages, which means if you just copy it and you send the same message, it works. But right now, what they do is they encode and randomize it, such that every time there's a new signal, and there is a new signature handshake between the door and the key. So next time, if you copy it, even it will not open because there's a new message being created, right? Good. But the key emphasis I want to show here is that these couple of examples and the other ones as well. The reason for the security challenge or vulnerability is because there is some sort of a shared resource and communication, right? Now, are these going to go away for embedded systems? No, we will always be sharing resources and communicating. And in fact, we are increasing this more towards autonomy, right? As we have seen in lecture 1 examples, right? So the challenge is going to be harder and harder and harder, right? So we need to find solutions for it. Okay? Good. So I can give you like a 1-minute break until I switch slides.
Yeah.
واحد يمكن مشاكل بعدين تقول
جزء صحيح.
وين عندك تدري أنا هاي هذا شيء كبير هذا أنا بس يا شباب
Okay. So after going through some of the challenges and opportunities and the bigger theme of a modern embedded system, we'll start taking the system layer by layer, starting from software programming and then sensors, actuators, I/Os, multi-cores, and all that stuff, and then discuss how we can address these challenges, right? From a technical perspective. So the reason I started by embedded software is because this is what you'll be doing in all the labs. Starting from lab 1, you will be really writing software to control the embedded system, and you'll be doing this in C, right? So why it's good to really revisit some of the software development techniques and aspects for an embedded system. Now, I know that you have already taken programming courses, including C and C++ and all that stuff. So hopefully that's not new to you. Also in 241, you did really program, I think, BIC using assembly and C or only assembly and C, right? You did this as well. But it's always important to think about if I have already taken a programming course. The programming course was intended more towards a general purpose system, right? Now, is there any difference when I move from a general purpose system to an embedded system? Right? So are there some considerations that I should maybe care about more, right? And as we will see in today's lecture, there are many considerations you have to put in mind when you are writing programs for embedded systems that usually you don't care about when you really write programs for general purpose systems, right? Good. So the first one is what we call a programming model, right? I think in your general programming course in second year, well, you have an IDE in your laptop, you write source code, you compile it, and then you run the binary and see that, right? What is really happening there is your target platform is the same platform that you are using for development, right? So it's just the same laptop. Now in 241, that's not the case. 241, if you remember correctly, you used an IDE in a desktop or laptop, right? And then you write your program, you compile it, you obtain a hex file, right? Which is your binary code, and then what do? You load it to the embedded system, right? Which means your target platform is different from the platform that you use for development. First of all, why that's the case? Why this was needed? Did you ever ask why should just go through this hassle? Why I really don't do whatever we did in our normal programming course when my target platform is the same as the host platform? Yeah. Yeah, but wouldn't it be more portable if I just really have the embedded system and write the software directly into it?
Not for like, sorry, not portability, like making it more lightweight.
Yeah, you're in the right track, which basically, yeah.
We can simulate the code before implementing it on the system.
An excellent point. And why we cannot really simulate it if we are developing an embedded system? Because of the ability constraint. Yeah, all the three are, if you are really saying the same thing. So the key idea is the embedded system is very resource constrained. It does not allow you to run like a GUI IDE that you can simulate stuff and look into the result and then burn it there, right? It will only take the bare metal application binary and execute it for you. So you need something that you can play around with, try different things, simulate, target different embedded platforms. And then once you are done testing and development, you just go and burn it there, right? So we call this the host target model for programming, right? You are using a host for development that is different than your eventual target, right? Now, to enable this, your laptop is mostly an Intel machine or AMD machine, so it's an x86 like ISA, right? Like in first lecture, we talked about instruction set arithmetic. Your platform, well, in 241, it was a BIC, which is definitely a RISC microarchitecture. These days, it's an ARM, right, which is also a RISC micro. It's just different ISA. Can I really write a program for an ISA and then target a different ISA? This is a little bit against what we said in lecture 0, right? Is that the compiler should be aware of the eventual ISA that you are targeting. So how, in fact, this was possible? Do you ever think of that?
The compiler, the IDE we use has the ISA for the
Yeah.
target.
For the target machine, so it's asking you what is your target machine, and they do a process called cross compilation, right? So in the background, there is a very complex process that the compiler is doing for you through the IDE. So what this says, okay, right now I'm going to execute and simulate this code in an x86 machine. But at the end, when I create the hex file, the assembly, and the binary, I'm going to create it for an ARM machine, for example, right? This is called cross compilation, right? Without cross compilation, we couldn't, in fact, do any of this because you cannot really write software in a machine and you are targeting a different machine unless it's the same IC. Good. These are some of the challenges that comes to embedded systems that you never think about when you talk about a general purpose system. Right? So if you move to a more powerful embedded system, something like a Raspberry Pi or NVIDIA Nano GPU or a system on a chip, well, this enables you really to develop on the same platform, right? So we call this the standalone model, where your host and target is the same, pretty much the same as the general purpose system, right? Why? Because in Raspberry Pi, for instance, you have an operating system, Raspbian, that really hook it up into a monitor and then write your development and testing and everything on the same platform, right? So again, this wasn't possible in, for example, our Nucleo board because, well, it's not as powerful as a Raspberry Pi, right? It cannot really enable you to run this IDE. Okay. Some of the other, maybe we should discuss this a little bit before you look into the slide. So there are some other few challenges when it comes to embedded systems. So let's try to reflect on the differences between embedded systems and general purpose systems that we had in the previous 2 lectures, and think of how does this really impact programming if you write programs for an embedded system. What are some of the things that will come to your mind where, well, I should be aware of what I'm really doing for an embedded system because of few characteristics for an embedded system?
Programs really need to be optimized. I cannot have millions of lines of code in an embedded system.
Excellent.
To do the same task, but with much less lines of code.
Yeah, excellent. And the reason for this is an embedded system.
Memory space.
Yeah, memory space, usually resource constrained, right? So we call embedded systems resource constrained devices compared to your laptop, for example, or this. So you have to be aware of the resource, right? And we will see some of the implications, how you pick up your data types, how you really define your memory behavior, that stuff, right? So that's one of the things to keep in mind, which is the most important one, by the way. So thank you. So some other is in an embedded system, you in fact, most of the time have a lower access to the hardware, right? So if you look into your big programming experience for 241, you're interacting directly with the hardware, right? So some of the times, for example, to enable an interrupt or to enable a GPIO, you go to a particular register in the memory, right? And then mask a certain bit to make it like an input port or an output port, right? But if you think about this low level programmability, you will never be able to do this in your laptop. In your laptop, you will never say, I want to access the register that is really controlling my mouse input port and then turn it out to be output. That's not there, right? You will always have layers of libraries and firmware and things that are really built for you, right? So in an embedded system, well, in your past experience, there was no even an operating system. Your program was directly interacting with the hardware, right? And interacting with the hardware at the bit level, right? So this low-level control of an embedded system is one of the features for embedded system programming compared to a general purpose program. How this is really important or how does it really impact an embedded system engineer, we will also discuss this. The third thing is compared to general purpose systems where in fact all the system on a chip or processors more or less kind of converted to few options, either it's like even like an ARM mobile application programming or your laptops and desktops are mostly x86 machines, whether they are AMD or Intel. In embedded, there are so many companies, so many platforms, right? Last time we said ARM is the dominant, that's true. But even with ARM is not really a manufacturing company. They are a licensed company. They give companies the cores, and then the companies the SoCs. For example, the board we are using in this lab, from which company it is? You know, like the 14411, ST Microelectronics, right? That's one of the companies manufacturing chips for embedded systems. I think in lecture, last lecture or the lecture before, we had a video from Texas Instruments, right? This is also NXP. There are Infineon, many companies that are building hardware for embedded systems, and each company has its own SoC, IDE, way of writing software, way of laying down the memory in the what we call a memory mapping. So this diversity on the market, which is not the case for general purpose systems, makes it very hard to really, well, write a portable code, because the code that runs for your ID in BEC is different than, well, BEC is different, I say, so it's a harder example. But even in your second year, if you had a different, like an ARM core, but a different platform than the ST Microelectronics, like another Texas Instrument board, for example, your ID will be different. The way you write code will be slightly different, right? So it's very hard to really develop something that is standardized in an embedded system, right? Now, when it comes to a programming language, one of the differences for an embedded system compared to a general purpose system, but there are so many high-level programming languages for general purpose systems. What is the most famous one? Python nowadays, yeah. Well, every 10 years, maybe you have a different language, right? But C also is very common, right? C++, Java, JavaScript, C#, whatever language, there's so many languages, right? But what about embedded systems? They are mostly C, right? So what is the reason? Very fast, yeah, very efficient, and gives you the low access control. We'll have a few of these discussions here. But one of the differences is many programming languages in general purpose systems, there are very few in embedded, and they are mostly C, right? Like most of the embedded systems are in fact programmed using C. Well, I think for you, I updated this thing. I'm opening an old slide, because this is the programming course I used to teach before. Basically, I was trying to make the link between what you guys have covered in earlier courses and what we do in this course. Simply, or ignore this code for now. It's more of your programming course. What is the code for your programming course? The C1?
C, 241, I think.
241?
I think.
No, 241 was the embedded interfacing one, right?
Like C++.
Yeah, that, C++.
So you mean the one for microcontroller?
No, the one for like C++, the general program.
Oh, okay, 120.
120, okay, yeah. So simply C is a very old language. It's from 70s, right? But the point is that it's still surviving up until now. It's one of the oldest, right? So why C is still surviving, even in general purpose systems? Why everything is bending on C? That's a very excellent point.
Fast.
Very fast, very performant, right? Like someone can say, some of you said Python is the most common, right? But if you, Python is now very common because of libraries and machine learning. If you look into all the machine learning frameworks right now, PyTorch or TensorFlow, name it, they are in fact written in, not in Python. They are written in C, right? Look, the Python is the interfacing one for you, right? What about operating systems? They are mostly C, right? That's also because of performance, right? So C is a very efficient language, right? This is why it's still surviving up until the moment. There is a very nice video here. I also added on your iLearn. Some of you might not know Linus, but Linus is in fact the inventor. I don't know if inventor is the right word for C, but he is simply the one with the C standardization, right? Do you know what else did you get that term before? Yes. Linux, right? It's coming from the name, right? Linux. Something else? Git. Yeah, excellent. Thank you. So this guy basically alone came up with C, Linux, and Git, right? Like I think this is more like a legion for computing systems, right? He has a very nice video here, interview. There is, well, the title, I can tell what he's going to say in the video from the title. Nothing is better than C, right? He's a very active caller for that C is in fact is the best language up until now, right? It's very nice C. So I think you should hopefully watch this video. Just broaden your mind about how people think about different languages. So we said it's already fast, efficient, and portable. Something for embedded systems especially. We said embedded systems usually give you a lower access to the hardware, right? Well, naturally it comes to C. Like C is the closest high-level programming language to assembly, right? First of all, what is really the closest to the machine? It's the machine code, right? Like machines don't really understand Java or Python or C or anything, just zeros and ones. What is above machine code? Assembly. That's the closest, right? In the past, well, when I was in my undergrad, I wrote my graduation project fully in assembly. It was like hundreds of code. It's a very, very tedious task, right? Not very human, but kind of natural way to do things and very, very slow to develop, right? But assembly is the closest to machine code. Now, if you look into all the high-level languages compared to assembly, the closest one to assembly is C, right? So C is the closest language that gives you control to the hardware. To the level that, in fact, in C, you can write assembly code. You can embed assembly inside C. Good. So naturally, C is more, more natural to use it for embedded because you need a hardware control, low-level hardware control, and C gives you this. And then an example of this close to machine thing is pointers. You guys have pointers, I think, in your yeah. So now in pointers, an aspect of C that does not exist in any other language, and it's in C++ because of C, but it does not exist in Java or Python or anything else, is you can directly access memory addresses using variables, right? So you can control memory manually as a programmer and allocate it and deallocate it, what we call dynamic memory allocation. There is no other language that can give you this, right? Someone can say, did you guys take Java? Any means? Yeah, I mean, there is basically a fallacy that says, well, references in Java are the same as pointers in C. Do you know references in Java? Good, because in last class, like someone said, references, they exist in Java, right? So simply does different. Pointers allows you to address a particular address in the network, right? Like I go there and write, I want to access location 0xFF3F, for example, right? Which is the register of the GPIO for, our port A, for example, in the controller, right? No other language enables you to do this. So that's a very big advantage. What is the disadvantage?
It's hard.
Very hard to code and also susceptible to human errors, right? In C, there is no garbage collector. So I need to allocate memory myself through pointers, but you also need to deallocate them. Otherwise, you'll have memory overflow and memory issues, right? Memory leaking. For this reason, as we'll see towards the end of the lecture, this next time, that in reality, most safety critical systems disallow by the certification to use any pointer or dynamic memory allocation, including software for automotive, for example. Which means if you are a software engineer, like a very software engineer for automotive following the AUTOSAR standard, I cannot write pointers. You cannot dynamically allocate memory. The reason is they are unsafe because they are susceptible to memory overflow, security vulnerabilities, and memory issues. Good. So these are some of the problems we just discussed right now. They are unsafe, enables leaking and undefined behavior, and you need a manual control of the dynamic. How much time do we have left? So I see you guys are. Yeah, we still have some time. Okay, so few slides that simply, yeah.
Yes, suppose you said dynamic memory allocation is not really used in what sense?
Not allowed in the high safety critical systems.
Okay.
Up until now, the standard disallows them, right? It tells you that your memory usage must be static, right? Just to have a defined behavior. Some of the things we said, I need a low-level hardware control, which means I need to access certain bits and certain registers. So you need to review really how we handle things. So as an embedded system engineer, you need to be aware of the type, like numbering systems who are mainly in binary. You need to access particular bits. We use a feature called bitwise manipulation a lot in embedded, right? To control certain bits in a register through masking. So this is like a few of these slides, I only have them there so that you have them when you study. Like you just refresh your mind about numbering systems, data types, and all that stuff. Now, data types in C, why it's important to review in embedded? Because your friend said I need to be very well optimized for memory, right? So assume, for example, I want to access certain bits in a register that I know there always be only be 8 bits. It doesn't make any sense that you define a variable that is an int, right? Because your int can be 32-bit. But you're only going to use 8 bits. So you're wasting, how many bits? 24 bits for no reason, right? 75% of your memory is wasted for this variable for no reason, right? So you need to be very aware of how you define your variables and types in in embedded, C, right, compared to C. Yeah, so if there is something that can really work for example, for a character or an integer, you don't go ahead and define a double, right? I used to teach a programming course for our students in MathMaster. It was first year programming course. In a general programming, it's always good also to talk about these things, how to be efficient in memory, how to be efficient in hardware. But in general purpose programming, people usually don't really care. They only care about the functionality. You have a very powerful machine anyway. So if you allocated 1 kilobyte more, nobody cares, right? But if you talk about an embedded system where your whole memory can be an 8 kilobyte memory, if you waste 1 kilobyte of memory in your application, that's very, very inefficient, right? So 1 kilobyte out of 8 is different than 1 kilobyte out of 4 gigs. Good. For example, if you're doing an embedded system engineer interview and they ask you to write a piece of a program, and then, well, the only thing you know about C is your general purpose C++ course. You define everything as a double. You'll never succeed this, right? Because you're not very efficient. Everything is 64-bit. You only have like a very small memory. You define 10 variables, you run out of memory. Your program will not run. Good. More than this, it's not only about data types, but also modifiers of the data types. So it's not only about defining a character, for example, because a character is 8 bits. But what if, for example, you are indexing a register? Generally, a character that is 8-bit allows both for signed and unsigned values, right? So if you have 8 bits, you go simply from negative 128 to a positive 127, right? But if you're indexing a register, you will never expect an index to be a negative, right? So it's more efficient to really have all your 8 bits dedicated to be positive numbers to enable a higher range. How do we do this?
That's
Unsigned, right? So defining an unsigned character allows you, using the exact same number of bits in the memory, to go from 0 to 255, right? So you doubled your range for your indexing without losing any extra bit in the memory, right? Using modifiers. Okay. This is why you will find very common in C, people are not really writing using any of these types. What they do is UNT8, UN16, UN32, right? Unsigned AND8, unsigned 8. So they put in the type, the width of the memory, right? Good. If I give you, for example, in a midterm or a final exam, and ask you to write a small piece of software, and then it requires you to write a UNT8, but then you define a double, know that there is a problem with your code. Right? Okay, good. Just a few examples, things. Something you should also know about what C allows and does not allow, like some undefined behavior in some of the variables. Yeah, maybe another note here about the types. So for example, an int, we usually say an int goes from 16 to 64-bit. Why an int has the variable width? Because it depends on the machine that you are targeting, right? Most of our modern machines, do you know how many, like what is the width of the registers in your laptops?
It's for
64, right? 32 were the old ones. I don't think any of you want like a 32-bit machine. I used to have a 32-bit machine like 12 years ago, right? But most of all the modern laptops, desktops, since maybe 10 years ago, are 64 bits, right? What about embedded systems? Do you know what was the width of your big chip in 241?
16 or 24, I don't think.
Okay, so what about Arduino? The smallest Arduino, which is the only one, is 8 bits, right? It's an 8-bit machine. So what does it mean? We call this the machine width. It means that all the registers in this chip is 8 bits, right? Well, there are 16-bit Arduinos, there are 32-bit Arduinos. What about ESP32? 32 from the name, right? It's called ESP32 because it has 32-bit registers. What about our device, like the Nucleo RGB board? It's a 64-bit ARM tools, which means it's like a lot, right, for an embedded system. It's one of the higher performance ones. Good. So why is it good to know these things? Because, for example, in the C standard, the width of an integer is in fact defined by the machine width, right? So if you really define something like int(x) and you put in a number and you try to execute this on ESP32 or an Arduino or in our ST device, then you will have a different width, right? Because the integer is variable based on the machine. People in embedded systems, and in fact, again, we'll see in the next lecture that the standard for safety critical systems, what we call the NCC, forces you not to use a variable end width. You must really put the width in the type. Why? To be deterministic, to be independent of the target machine. You have to tell me I'm using an N8 or an N16 or an N32 to make sure that your software always has a deterministic behavior. Okay? Good. I think we can stop here because otherwise I have a long example that will not be able to. Yeah, we have 1 minute. So let's stop here. We don't have a lecture on Thursday. Okay. So we'll continue this topic on next Tuesday. See you next.